In this video on trigonometry, we're going to measure diagonals, and we're going to look at what it means by keeping our answers in exact form. Okay, and I'm going to start just by thinking about the squares that we're working on here. If each square represents 1 centimetre, so they're 1 centimetre squares along each of the length of the sides of the square, then if I measure along the diagonal, what's the length going to be? Well, there are two ways of doing this. One would be to work with Pythagoras, which we'll do in a moment. The other would be simply to measure it. So let's start by measuring using a ruler. So if I look at this carefully, I think what I've got is, well, if I just make a dot here and say, well, what is the length from here to here? That seems to settle at 1.4. Okay, all right, let's remove our ruler. There we go, move that off. And we can write this then, it's a little triangle. So if I say that this is the legs of a right-angled triangle, these two are the legs, so-called, and the diagonal is the hypotenuse, then we put a little right-angle symbol here. We say this is 1, and this, we think, is 1.4, but I'm going to put question mark, because a ruler can't really give us a very accurate measurement, or can it? Let's put this to the test. So we're going to put it to the test by comparing to Pythagoras' theorem, or the Pythagorean Theorem, which hopefully you're already familiar with, but basically it says that if you have a right-angled triangle, so we just sketch a right-angled triangle here, then if this side, these two sides, these two legs are A and B, then the hypotenuse, the angle, the side, sorry, opposite the right angle, so the diagonal here, then C, or C squared, the square on the hypotenuse, is equal to the sum of the squares of the other two sides. In other words, is equal to A squared plus B squared. So that's the Pythagorean theorem. In the second part of the video, we'll have a go at proving it. But it's true, and so we can use the Pythagorean theorem to do all sorts of other things. It's an extremely useful, fundamental theorem idea. Okay, so by Pythagoras then, what we can do is say, well, A squared, let's write C squared again, C squared equals, A squared is 1, so that's 1 squared. B squared is 1, so that's 1 squared as well. And 1 squared is just 1, so we've got 1 plus 1 equals 2. If C squared is 2, what's C? Well, if we square root both sides of the equation, we end up with square root of C squared is obviously just C. Okay, so we just write this as C, and C equals the square root then of 2. But what's the square root of 2? Is it 1.4? Well, we know that it's exactly root 2, so we can just call this root 2. We know this is exactly root 2. If I plug in 1.4 into a calculator, just to save time, and square it, then what do I get? Well, if I convert it to decimal form, it gives me the answer of 1.96. So 1.4, here we go, 1.4 squared is not 2, it equals 1.96. And what if I tried something even more accurate? So if I use my calculator again and I get the square root of 2, so let's have another go. So if I type in square root 2 equals, now it just gives me square root 2 as the answer, and so I have to convert it to a decimal. It gives me this 1.4 4, 1, 4, 2. Well, at this point I can see that the numbers go on forever. They're not recurring, so they just keep going. So how accurate is that answer? Well, if I type in 1.41421 and square that, what do I get? Okay, squared. I need to remove those dots. Okay. Let's have another go. There we go. So 1.41421 squared equals 1.9999. So we're not getting to 2 still. 8929924. Okay, so we get this horrible string of numbers. We can keep going. We could try 143. Let's have a go at that quickly. So 1.4143 squared. Now this time we've got 2, but 0.000244449. Now we'll never get to 2 by this method. However long we make our string of decimals, there'll always be other numbers that because it goes on forever. And so it's sensible not to worry about decimals, which is based on our base 10 system, and our base 10 system clearly doesn't work very effectively for these kind of trigonometric systems. So sometimes you'll want to convert it to decimals, but where possible we should leave it like this, which is called leaving it in exact form or surd form. Okay, because any number which has these recurring decimals is actually an irrational number, can't be expressed as a whole number or a fraction. An irrational number is known as a surd. Okay, so surds give us a way of representing the answer in exact form, and we just leave the square root symbol there. So the answer is c equals root 2. Okay, if that's our first problem, let's have a go at another one and keep looking at this question of exact form and surds. So this time what I'm going to do is draw a line from here to here, like that, which means that our legs must be 3 and 2. So c squared again is what we're trying to find. So this is c, but we're using Pythagoras. C squared equals a squared, well that's 3 squared, plus b squared, which is 2 squared. And 3 squared is 9, 2 squared is 4, so 9 plus 4, 13. What then is c? C must therefore be the square root of 13, or we just say root 13. And again, we leave it in surd form, in exact form, because that's completely accurate in that form, and if we convert it to a decimal, we'll introduce tiny but maybe significant inaccuracies. So we won't do that, leaving it in exact form. Now before we move on to another problem, what I want to do now is just do a check. What exactly is root 13? Let's just think about that for a minute. What if we estimate root 13 as a check to see whether that's a plausible answer, because we might well have made a mistake somewhere in our calculation. So if we estimate root 13, the only way to do this is to think of, well, what's a lower square root that we do know the answer to? If we think of root 9, like that, square root of 9, as we know, is 3. And the next one is going to be the square root of 16, which gives us an integer. So the square root of 16 is going to give us 4. Therefore, our estimate of the square root of 13 is going to be 3, well, in the middle here, 3.5. It's not in equals, though, as we've seen. None of these decimal answers can be accurate, so we have to make sure we say approximately equal to 3.5. And that's a really nice little check. If we look at our A value here, this side length here, then this length here is 3. The hypotenuse has got to be longer, slightly longer, because it's at an angle. And so 3.5 sounds about right. So if root 13 is approximately equal to 3.5, then our answer that c equals the square root of 13 is most likely correct. Okay, so always a good idea to do a check, make sure we haven't made any slips, and this is a good way of doing it. Find the root that's going to give us a whole number below, in this case 13, and above gives us root 9, root 16, 3 and 4, and the estimate there is between 3 and 4, 3.5. So that's a good way of checking. Okay, let's do another one. So see, what should we do now? Let's keep it nice and straightforward. Let's just measure from here now to here. This would actually give us a 30-degree angle. Okay, so again, C and our legs, well, 2 and 1. So again, by Pythagoras, c squared equals 1 squared. So taking this as a this time, doesn't matter which order. 1 squared plus 2 squared. 1 squared is 1, 2 squared is 4, so it's 1 plus 4, 5. C must therefore be root 5, which is in exact form, so we leave it exactly. But what is this a plausible answer? Let's just estimate. There we go. So below this we have root 4. So root 4 we know is 2. And above this, well, the next one is going to be the square root of 9, giving us an integer of 3. So our estimate would be that the square root of 5 is approximately equal to, not equal to. Very important that we remember always, not to write the equal sign, but to write approximately equal to. Otherwise we'll be writing an incorrect statement. So square root of 5 must be approximately equal to 2.5, halfway between 2 and 3. And again, looking at our diagram, if this is 2, then this must be slightly longer, 2.5, and so that seems correct. But this, remember, is not the exact answer. C does not equal 2.5, it does equal root 5. So do just a couple more. And this time what I'm going to do is, let's just mix it up a little bit. So yeah, if I fit that in here, okay. This time I'm not going to draw this to scale, and very often you'll see this written not to scale, which frees up our drawing. We can just draw a triangle however we want. Make it slightly plausible, I suppose. But the lengths don't correspond anymore to the square paper that we were using. So this time, if I label this C, why not define the lengths here then? Instead of integers, let's use these surds. So irrational numbers. So for example, let's say root 6, and this one, let's say root 5. So how would that work out? Well, again, by Pythagoras, c squared equals a squared, well, that's root 5, all squared, plus root 6, there we go, all squared. And what would that be? Well, this looks a bit confusing, but if you think about it, the square root of 5 takes it in one direction, roots it. and then squares it again, it must go back to 5. So the square root of 5 squared equals 5, and the square root of 6 squared must equal 6. 5 plus 6 equals 11, therefore C equals root 11, and that's, again, the exact answer. We're not therefore going to convert it to decimals. We are though going to do another estimate, so it's always worth doing this, even though it takes a few minutes. It doesn't really take very long, and we can be confident of our answer. So what's below the square root of 11? Well, we have the square root of 9, which is 3, and the square root of 16 gives us 4. Therefore, the square root of 11 must be approximately equal to, there we go, approximately equal to 3.5. And again, it's trickier this time to do our estimate, but it sounds about right, because if I think about the square root of 6 here, well, the square root of 6 is between the square root of 4 and the square root of 9. In other words, it's between 2 and 3. So that's going to be estimated at 2.5. So approximately equal to 2.5. And this is also, it's going to be a bit less than that. So let's say that's approximately equal to 2.3. So again, if I think of 2.3, 2.5, that's going to be quite a bit longer. It is going to be probably larger than 3, and so square root of 11 sounds plausible. I'm going to say that's correct. Okay, now there's another variation on this that we ought to just explore, and that's when you're actually given the hypotenuse. So if we have our diagonal here, and let's use some larger numbers here, so really not to scale this time, square root of 17. Okay, so that can't be broken up any further. Again, it's in exact form. And let's just have an integer on this side. So let's say 4. So this time, instead of trying to find C, the diagonal, we're trying to find A, one of the legs. Okay. Well, no problem. We just use C squared equals A squared plus B squared again, but we'll rearrange it. So if C squared equals A squared plus B squared, we can say A squared, subtract B squared from both sides, must equal C squared minus B squared. Okay. Now we plug in our values. So A squared is what we're trying to find. C squared is going to be root 17 squared minus B squared. Well, B is 4, so that's 4 squared. Don't need brackets for this one. Okay, so 4 squared. And if we just sort this out, we get 17. Root 17 squared is 17 minus 16. So A squared, well, that works out very nicely. A squared is equal to 1. Well, the square root of 1 is simply 1. So therefore, A equals 1. Okay? Well, again, we can just do a little check. Is that plausible? Square root of 17 is what we want to check this time. Okay, and we're expecting the square root of 17 to be, well, larger than 4, otherwise this triangle wouldn't work. So let's just estimate root 17. Well, root 16 we know is 4, so it's going to be slightly more than 4. So therefore we can say square root of 17 is going to be approximately equal to, let's say, 4.2. And again, we're just looking at this length here. If we've got 4.2 here and 4 here, then we're only going to have a small gap here. So 1 sounds about right. So I'm going to say that's correct. One final problem. Sometimes you might get something like this. So if I draw going up through the diagonal here, what we've got here is a 45-degree angle, and if we've got a 45-degree angle, then what we're going to get is an isosceles triangle. In other words, these two sides are the same. So in this situation, let's choose some numbers. Let's say we had, well, let's use a compound surd. So we have 2 root 2. Okay, so 2 times root 2 as our diagonal or hypotenuse. Then A, and this side B, we're going to have A equals B and B equals A. So we can say that B equals A, both sides equal A. Let's just write this down then nice and clearly. So C squared we know is 2 root 2 squared equal to A squared plus A squared. In other words, what have we got here? 2A squared. Okay, now we can sort this one out a little bit, and we can move it maybe onto the right hand side. So if we square 2, what do we get? We get 4, and we square root 2, we get 2. So we've got 4 times 2, which is going to be 8. On the left hand side we're going to have 2a squared, but if I divide both sides by 2, then I'm going to have 2a squared divided by 2, like that. Cancel those 2's, just a squared on the left hand side, and I'm going to have 4 times 2 divided by 2 equals 8 divided by 2 equals 4. Okay, and if a squared equals 4, this again works out very neatly. It won't always work out as neatly as this, but sometimes they do. We can say, therefore, if I square root both sides, a equals the square root of 4, root 4, and this time we don't leave it in the exact form. We're going to say a equals 2. Okay. And lastly, to check if this answer is plausible or not, what I'm going to do is work the other way. So in other words, what I'm going to go back to is my c squared equals a squared plus b squared. So c squared equals, now we've got the answer 2. Let's try that. So 2 squared plus 2 squared. In other words, 4 plus 4 equals 8. Therefore c, okay, equals root 8. Now, root 8 is not the same as 2 root 2, or it doesn't seem to be the same, but that's because there's something else that we need to do to a root like this. Whenever we can simplify it to make the number underneath the square root sign smaller, in this case making it root 2, then we should. And root 8 is a classic example of this. Root 12 would be another. What we can do with root 8 is we can express that instead as equal to 4 times 2, because 4 times 2 is 8. So in other words, what I've seen underneath the root sign here is a square number, 4. And so by factorizing it, so we've got 4 times 2 under the square root sign, I can then do this. I can say, well, that's the same as the square root of 4 times the square root of 2. Well, the square root of 4 is 2, so square root of 4, 2 times root 2. So root 8 is better expressed as 2 root 2, and so that's a good check, and so that we know that our answer, a equals 2, must be correct. A and b equal 2. Okay, finally, what I'm going to do is look at how to place the surds on the real number line. And here we've got the real number line, so it's the rational numbers and the irrational numbers, including fractions, but not just fractions, but also surds. I'm going to show you how to plot those on the number line. So to start with, let's just think about what we're dealing with here. So if we start by thinking about root 1, okay, root 1 is obviously 1. So we've already got that on a number line, we don't need to worry about that. The next one I want to do though is root 2. Okay? So how am I going to plot root 2? Well, if I go up here, 1, then I've got 1 as my A, 1 as my B, and if I draw the diagonal here, C, well, C squared is going to be 1 squared plus 1 squared, that's going to be 2, and so this must be root 2. So to get root 2 on the number line, all I've got to do is pull that down and mark it off. So that must be where root 2 lies. Okay, let's move on to root 3. Well, root 3, okay, root 3 is going to be a little further along, but it's not going to be as far along as root 4, which is 2. Okay, let's put commas between these. So, to construct root 3, I'm going to go up from root 2, which is here. So that what we've got now is a length of root 2 squared plus 1 squared, giving me 2 plus 1, 3 for my diagonal. Let's draw that along there. So this must be root 3, and if I bring that down, mark it off, there we've now got root 3. So root 4 is done. The next surd to map on here, root 5. I'm not going to do all of them, but just to show you how this works. Okay, so going up from 2, draw my diagonal. What have I got? I've got 2 squared plus 1 squared gives me 5 squared, so this must be root 5. Bring it down then and mark it off. There we go. So root 6. Now root 6 could be made by, again, drawing up from here, drawing the diagonal, and that's going to be, when I bring it down, a way to mark off root 6, because I would have 2 squared, sorry, not 2 squared, I have root 5 squared, so it would be 5 plus 1 squared, which would be 6, and so that would give me my root 6 about there. But I'm going to do it a slightly different way this time. What I'm going to do is draw it up from here, which is root 2. Okay, so what I've got, if I just draw this out quickly, so what I've got here now must be root 2. Along this side here, what I've got here is 2. So a squared plus b squared is going to give me 2 plus 4. So again, this is another way of getting root 6, because this length must be root 6. Let's just draw that along there. There we go. Bring that down, mark it off. So 2 ways there of finding root 6. So we've got root 6. And finally, if we just think about, well, where's root 7 going to be? Root 7 is going to be about here, root 8 is going to be about here, and here we're going to get 3, in other words, root 9, and so on. So these surds really complete, or help to complete, what we call the real number line. Okay, the real number line, which is a continuum. In other words, it comprises all numbers, including the natural numbers, the integers, which of course are 1, 2, 3, 4, 5, but also 0 and the negative numbers. But we're also going to add now the well, if we're thinking about the fractions, things like let's say 4/5. So if we do these above, and of course there are as many fractions as you want, but if we think of, I don't know, something like 22, so an improper fraction as well, 22/7. You can express, just as you can express 2 as surds, you can express that as a fraction as well. So that would be 2, 2. So these are called the rational numbers. But what we're dealing with now is we're adding the surds and all irrational numbers, so plus irrational numbers, and we get the real numbers. So finally, we've got all numbers, or have we? We've got all real numbers, but there are also something called imaginary numbers. But I think at this stage we'll just leave it as working with real numbers, and they're completed very much by addition of the surds. So we've now got